Welcome to the Explainer. You know, in chemistry, some reactions just race to the finish line, while others, they kind of seem to give up halfway. So why is that? Today, we're going to build a predictive tool, like a GPS for chemical reactions, that can tell us not just where a reaction is headed, but exactly why it stops when it does.
All right, so let's dig into the central puzzle. You mix some chemicals together and you're expecting them all to turn into your final product, but sometimes the reaction just stops. What's going on? Well, it's because most reactions are actually reversible. It's like a constant tug of war between the ingredients you start with, the reactants, and the stuff you end up with, the product.
So to really get a handle on this balance, this sort of chemical crossroads, we need a way to check in on the reaction's progress, right? We need a snapshot that tells us, okay, right now, in this very moment, how much product do we have versus how much of the original stuff is left?
And that snapshot has a name. It's called the reaction quotient, but we're just going to call it Q. It's just a single, really powerful number that gives us the exact ratio of products to reactants at any given moment.
Now, the beautiful thing about Q is that we don't have to guess. We build this mathematical formula directly from the balanced chemical equation. Just think of it like a fraction. You put the products on top in the numerator and the reactants on the bottom in the denominator. And this is the really key part, you use the balancing numbers from the equation as exponents. It's that simple. That's what makes sure the ratio is properly weighted.
So let's look at these examples right from our source material. See how this works? For the reaction that makes ozone, the product, O3, is on top, and it's squared because of the 2 in the balanced equation. The reactant, O2, is on the bottom, and it's cubed because of the 3. You see? It's a direct translation from the chemistry to the math.
Okay, now here's where it gets really cool. As a reaction moves along, the value of Q doesn't just wander around randomly. No, it's moving with a purpose. It is heading toward a very, very specific destination. So just imagine two different experiments for the exact same reaction. In the first one, we start with only reactants, no products yet. So the top of our Q fraction is 0, which means Q is 0. In the second experiment, we do the opposite. We start with only products. Now the bottom of our Q fraction is 0, and as you know, dividing by 0 in math gives you, well, basically an infinitely large number. So we have two totally opposite starting points, 0 and infinity.
And here is the amazing part. Even though they started at these two completely different extremes, both reactions will chug along, one going forward, the other in reverse, until they reach the exact same ratio of products to reactants. It doesn't matter where they start, they are driving towards the same destination.
This final destination, this very specific fixed value of Q that every reversible reaction is trying to get to, it has a special name. It's the equilibrium constant, or just K. It's that sweet spot where the forward and reverse reactions are happening at the exact same rate, and that whole tug of war is perfectly balanced.
This incredible idea is known as the law of mass action. It's a fundamental rule of the universe, really. It guarantees that for any given reaction at a certain temperature, there is one and only one destination, K, where that system will find its balance.
So this brings us to the whole point of this. If we know the destination, K, and we know our current location, Q, we can actually predict the future. We can figure out exactly which way the reaction has to go to find its balance.
This is our chemical GPS. If your current spot, Q, is a smaller number than your destination, K, it just means you don't have enough products yet. The GPS tells you, proceed forward. If Q is bigger than K, you've overshot the mark and you have too many products. Your GPS says, proceed in reverse. And if Q equals K, well, you've arrived. You are at your destination, equilibrium.
All right, let's put this GPS to the test with a real example from our source material, the reaction where nitrogen dioxide turns into dinitrogen tetroxide. So, right at the very beginning, all we have is the reactant, NO2. Since there's no product at all, the top of our Q fraction is 0, which means our journey starts with Q being equal to 0.
Now through experiments, we know that the destination for this reaction, K, is 160. Our starting point, Q, is 0. Obviously, 0 is way less than 160, so our chemical GPS gives us crystal clear directions. The reaction is going to move forward. It's going to make more product, which will cause Q to climb up and up, until it finally hits its destination of 160.
You know, the size of K also tells you a lot. A really big K, like 160 or even bigger, means the reaction heavily favors making products. The final mix is going to be almost all product. A tiny K, something close to 0, tells you the reaction barely gets going at all, leaving you with mostly reactants. And a K somewhere around 1, that tells you the destination is a pretty even mix of both.
So far, we've kind of assumed all our chemicals are in the same state, like they're all gases. But what happens to our GPS when the road conditions change? What if we're mixing solids with gases?
So, how does our GPS handle a mix of, say, solids, liquids, and gases all in one reaction? You might think that makes things way more complicated, but actually, it's kind of the opposite.
Yeah, this situation is called a heterogeneous equilibrium. And while that sounds all fancy and complex, it actually introduces a really simple rule that makes our calculations even easier.
The rule is just this. When you build your expression for Q or K, you just leave out any pure solids and pure liquids. I mean, think about it. The concentration of a solid chunk of rock or a puddle of water doesn't really change, right? It's constant. So chemists just kind of bundle that constant effect into the K value itself. It just cleans up the math.
This example just shows it perfectly. You have a limestone, a solid, decomposing into another solid and a gas. We get to just ignore both of the solids. So the entire balance point of this reaction, its destination K, depends only on the amount of one single thing, the carbon dioxide gas. It makes everything so much simpler.
So there you have it. We built this incredibly powerful GPS for chemistry. By comparing a snapshot of our reaction, Q, to its fixed destination, K, we can predict its path. But that leaves us with one last, pretty fascinating question to think about. The destination, K, is a constant. But what would it actually take to move the destination itself? Well, that's a story for another time.